finally we are at the most important day of the whole semester. That's today. Well, actually, it's the first day that we're going to formally talk about equilibrium. There's going to be all kinds of really great stuff that we're going to do here, and your abilities to conduct real analyses of real systems are just going to explode after today. Right now, the systems that we're going to work through are going to have members, structural members in them, that ultimately are going to either be in tension, being pulled, right, pulled like the rubber band here, or they're going to be squeezed in compression, right? So that would be pushing them things together, right? Of course, that same member that I just squeezed could also be pulled. So we'll talk about some of these members that can only do one of these things as we go along. Now, one thing we're going to ignore if a member does go into compression is that little instability that just happened. That's called buckling, and we're going to ignore that. We're going to focus on members that only can be purely squeezed without that buckling, or stretched without any problems either. Right? We're going to go through several contexts. I want you to pay attention to what happens with all these little force arrows that are running around in our free body diagrams. Here we have a drawing of a member. The member is being pulled, so it's in tension. Note that any body that is in tension is going to have its force arrow going away from the body, no matter which side we're talking about. If it's in compression, the force arrow goes towards the body. Cables and ropes are ones that can only be subjected to tension, because otherwise they buckle, phenomenon that we're going to try to not include at this point. Right, so context-wise here, I want you to take note here that here we've got this cable, three-dimensional cable hoist system with this car down here. Its self-weight is what's driving the whole system. And then we've got a free body diagram that we're going to create by cutting around this little hook part, and we're going to free out this cable. The effect of that cable supporting that hoist hook is going upwards here, and then we have the four cables down there. Remember, cables, ropes only can go away from the body, so we have these four ones all coming out here. Notice something, I won't give you the answer, but notice something about the geometry of all five of those force arrows, particularly their lines of action. Down below, what we've got is a small segment of the roof system for the speed skating oval down in Kearns, Utah. This roof system has a whole series of parallel two-dimensional pieces where we got this little big old gigantic spar, we call it. We've got cables coming off of that spar, and then what you can't see on the edge of this is what you actually have here. Right? So this one is the same as the one that you do see, and we're going to just focus on this little joint. You got this little post coming out here. Really, it's another spar that comes out here. You got a cable that way, and when we cut that free body diagram, remember, cables are in tension, going away from the body. This big thick thing that can take compression, just like this little beam could before, right? That can push on the joint, so it's going towards the free body, right? Ooh, notice we're talking about lines of actions and forces, and we're talking about these free body diagrams. All really good stuff. Here is a gusset plate system where two diagonal members are framing into a joint. These dashed lines indicate the longitudinal axis of the member, and the lines of the action of the forces are going to go right through there. These are actually internal forces associated with these particular two pieces, which are actually a representation of what we call in steel shapes angles. Angles have a cross-section that look like an L, an L. Two pieces of steel kind of joined together, creating a right angle usually. Right? And those forces pass through a common point, in this case called a working point. Here we have an anchor into a floor system, and we've got three different tensile type forces that are associated with cables hooked to this anchor. And notice there that all of those forces are passing through this little origin. Yet another system here where we have a hoist system, two different cables, one wrapping over the pulley at B, coming down tied off at A, another one wrapped over the pulley at C, tied off at A. And then we have the hanger rope that is coming off of A that goes down to this crate. And these two laborers are lifting the hoist through this kind of a assembly. And we take a little close-in free body diagram here of that particular location. Let me zoom in. And we've got then cables. We're cutting right around here, creating the free body diagram. There's our point A, and tension in one cable, tension in another cable, tension in the third cable, and this force triangle will be a statement of equilibrium. That's where we actually are headed. That in equilibrium, we don't have any acceleration, so the net balance of things, F equals ma kind of thing, no acceleration, means that all the sum of those forces must be zero, and that's vectorially, how would we represent, vectorially and rather graphically, how we represent what's going on with those three forces. We'll get into more of that in just a bit. And then one more example before we formalize some things, and then we charge off into an example. We've got this lifting system, again, a pulley that wraps, sorry, a rope cable that wraps around the pulley at the end of the boom, comes down, is tied off at C. We've got this 1,200 pound weight here, and then another person trying to help control what's going on. They got a cable attached and pulling on that thing, and so when we do a free body diagram around that joint, then we've got these three forces that note a couple of things. One, all of these forces, these internal forces, that's internal to the body, are directed along the longitudinal axis, or the straight line point between the two ends of that particular member. Right? So the line of action of the force is same as the longitudinal axis of the member when we're creating these free body diagrams. Now, even the more important thing is, if you were to go back in the video, don't do it yet. If you go back in the video and you look at every single one of these free body diagrams, these lines of actions of the forces will all pass through a common point, and that's what we call a concurrent force system. That all lines of action pass through common point. And when that is the case, then our statement of equilibrium of that system is going to be the sum of all of the forces as force vectors is going to be equal to zero. We have no acceleration anymore. Now that's a one single vector equation. What that means in scalar form are two equations in 2D. That is, all the x components of the forces must be equal to zero. All of the y components must sum to be equal to zero. So we can have acceleration in the x direction, which we're setting to zero, or acceleration in the another direction, the y, setting that equal to zero. This would be the sum of all those kinds of things, and that's what leads us to that little force triangle that we had in the previous one. Now you can go back, so to speak, right? These all three have to then come back to where we started, no matter which one we start with first. We'll come back to the beginning point of that. That closes off as one complete force polygon. Right? Next, we're going to go do some real calculations.